Welcome to lesson number 27, and today we're looking at the limits of trig functions. So by the end of this lesson, and once you get through the homework, you should be able to explain and apply the concept of limits when sine and cosine are involved. So up to this point, all we've done so far is limits involving polynomials and rational functions. And in order to do derivatives, you need to be able to understand how limits work. So now that we've finished the discussion on limits for polynomials and rational functions, we're going to move on to the discussion on limits of trig functions so that we can end up taking the derivative of trig functions. So what I've got for us here today, I'm going to actually show you how the primary trig limit was developed here. So below here, you copy the note as we go, and I'm going to talk about it. And keep in mind that all angles are in radians. So for the first triangle here in the diagram, we want to find the area of triangle AOP. So we're looking for the red shaded area here. It's a right triangle. Area of a triangle is given by 1/2 base times height. So what are the base and the height? Well, the base is side OP, and the height is side AP. So because we've used vectors, we know what the radius or the hypotenuse length is. It's going to be R, and we know the angle. So we can use our knowledge of vectors to find the missing sides. So side OP is just going to be R cos theta, and AP is going to be R sine theta. So that's our base and our height. So that's how I get the R cos theta and R sine theta. And when you multiply those together, you end up with 1/2 R squared sine theta cos theta. So that's the area of our triangle AOP. All right, moving down. I don't think you've had to find the area of a sector before, but a sector is just a piece of pie. So the area of a piece of pie. And I'm just going to give you the formula for a sector is 1/2 R squared theta. And again, remember that theta is measured in radians. And finally, the third one wants us to find the area of the large triangle. So here's our large triangle, QOB. And the one thing we got to keep in mind from question number 2, we said that OA is the radius of a circle. If I was to spin that around, it would create a circle. So that means if it came down to this point here, point B, that this length, OB, is also R in length. Okay, so because of area 2, or the area of the second area here, we know that the pi, if the pi length, if it's a piece of pie, then the sides of all sides of the pie, or the inside pieces, have to be a length of R. So that being said, we know that it's a right angle triangle. I now know that the base is going to have a length of R. So that's how I get that. Now, how do we get the height, QB? The height QB is taken from our primary trig ratio tan. So we're looking for opposite over adjacent. The opposite side is the height, H, and the adjacent side is length R. Isolating for H, we get H is equal to R tan theta. So there's the substitution, 1/2 R times R tan theta, and that tells us that the area of that larger triangle is 1/2 R squared tan theta. So there are the three areas. So before I move on to the next slide, I want to ask you, compare the areas of these shapes. And hopefully most of you are saying that this is the smallest area, and this one down here at the bottom is our largest, which puts the middle one, the second one, in the middle. All right. So that being said, then, we're going to compare the three areas as a ratio. So very similar to how we did it in grade 9 with the volume or surface area of various shapes. So we're going to compare the areas of our three shapes. So I wrote the original three areas out, and when you look at them, each one had a 1/2. All right, and each one had an R squared. So because they're all common to all three ratios, I can cancel them out in the R squared. They all cancel out, and we get it reduced down to just sine theta, cos theta, just theta for the middle ratio, and the last term is going to be sine theta over cos theta. So my next step, I'm going to divide all three of those by sine theta. And the reason is just because the first and last one will have only cos in it, and the middle one will just have sine. So we've isolated sine, cos, and tan. And what happens is it looks like this. So we end up with a 3-term ratio that looks like that. Now what I want to do is I want to compare these, and I want to return back to area. So in terms of area, you told me that AOP was the small triangle, so it should be the smallest area. Okay? Which means this one is the middle area, and this one's the largest. So I set up the proportion signs. Okay, so I've jumped out of the ratio, and because we did the same thing to every term, it's maintained its value in magnitude. So that should be true. So if I then analyze each of these terms for theta getting really, really small, so theta going to 0, I'm going to do a limit analysis on each one. So the cos theta, I'm going to take the limit of cos theta as theta goes to 0. And similarly, I'll do it for the other two ratios. Okay, so I'm just doing a limit analysis. The first one, as theta goes to 0, so that would mean cos, what is cos of 0? Well, the answer is 1. The second one I don't want to do because sine theta, if theta is 0, sine of 0 is 0, and I can't deal with that yet, okay, because we're not sure how to divide by 0 there. And finally, the last one, if theta is 0, cos of 0 is 1, so that last fraction is 1. So when we look at this, this is kind of interesting, because according to this, since the first and last ratios were equal to 1, and the middle term has to fall in between, the only logical conclusion we can come up with is that, in fact, the limit as theta approaches 0 for theta divided by sine theta, it has to equal 1. That's the only logical conclusion. Now you're telling me, you're looking back at the three areas now and you're saying that's not possible, that doesn't even make any sense because they're three distinct shapes. How can they have the exact same area? This is the my get out of jail free card for you. This is only for very small values of theta. So if we create a very, 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 very small triangle, so when I'm talking about a very small triangle, I'm talking about a triangle that looks like this, such that you can't tell me exactly whether this is a curved end, so does it make up a sector, or is it the big triangle, and so on and so forth. So this only works for very, very small angles of theta. All right. So last thing then, I want to talk about the summary here. These two right here are the ones we just talked about or came up with in that area proof. And it's the same for the reciprocal. So theta divided by sine theta is the same as sine theta over theta. So they're in terms of reciprocal, they're the same. This one we had on the previous page, but this one's kind of obvious because there's no problem with this one. Okay, there's no issue with that one. You can just plug it in the calculator. It's the same for these two. You just plug it in the calculator, and it's an obvious. Once you sit down and analyze it, it's obvious because you just plug it in the calculator. There's no issues. This last one is a hybrid of the two up here. Okay, and the limit itself, it says that if n is multiplying theta, then, and this is also n theta, then you still have that proportional relationship. It remains the same. So n is an element of real numbers. Okay, so there's a summary of the various trig ratios that we're going to be applying, and I'm going to do a couple of examples here in a second for us to go through and follow through. And you're going to be, the trig ones are going to be a little bit more challenging again than polynomials and the rational. So you're going to have to take some patience when you're working through them. And it's one of those things that once you practice it and start seeing the pattern, it starts coming easier and easier. So I'm going to warn you up front before we jump in.